Alright, so welcome everybody. So this is to present a little bit an interface that I have developed in the last few months. So that's an interface that it's a grid, okay, and the idea is to simulate what is called a lattice gas on this grid. So this is made to be basically point and click style of let's say a tool, and this tool is made for understanding a little bit how let's say a liquid behaves, or let's say a set of particles like ink particles moving about in a fluid, or simply to understand how, for instance, there are phase changes between liquid and gas depending on the interactions we put between particles. So just to show how that works, basically you've got various buttons here that I will discuss a bit. Here you've got the various parameters actually of the simulation, and here you've got the main, that's basically the main event. So what happens is that everything is clickable. So you click here and a particle appears, you click there, a particle appears, you click there, etc. So you can put basically, you know, many particles, there is no problem. Here this indicates the number of particles you've put, and here this tells you what is called the packing fraction, but you can simply think of it as being the density of your blue particles. Okay, so once you've done that, you can simply click Start, and then the simulation will start running. So the simulation here is simply a Brownian simulation. So particles are equally likely to go left, right, up, or down, except if basically another particle is obstructing the particular path that the particle wants to take. So that's basically how this simulation works. I will stop just to mention a few things. So here, this is the actual energy of the system. So it turns out that the particles here actually interact. It's just that they don't interact strongly enough because I have a high temperature for them to aggregate into a fluid phase, if you will, or a liquid phase. So they are still in the gas phase. Here you can see an entropy, and this particular entropy is related to what you see actually here. So this frequency here is based on simply taking a virtual dividing surface here and basically asking the question, what is the probability that if I pick one of these blue particles at random, it will be either on the left hand side of this dividing line or on the right hand side. Okay, so if I ask myself this question, I can associate a particular probability that depends on the configuration, and that's what you see that is depicted here. And to this probability, one can associate a particular entropy that is called the Shannon entropy, and that you can see here. So that's how basically the thing works, and you can basically continue to increase. And the idea that I want to show here by increasing a little bit the number is to show that basically the fluctuations that you will observe here are actually smaller than they were before. Okay, so this is basically size effects, statistical size effects can be discussed as well in this context, and fluctuations of the entropy, of course, are smoothened as you do that. So that's one way to play. Now we can reset, and what we can do is actually there is a way to create droplets directly of ink, if you will. And so this is here, that's the smallest type of droplet you can create. Here this is a square-shaped droplet, but there are many others. Also, normally they have kind of disc shape, so you will see that in a minute. So this enables to create many particles at the same time. What you see here is that also the color changes for the energy and the entropy. And so if I restart the simulation again, It actually takes time because they were all stuck together, and there is, as I told you, a bit of energy. And what you see is that then you've got another plot that appears. I need to tell you here, so that's the actual energy of the system. That's the mean energy. That here is the variance, but that's related to the mean energy. And the reason why it's zero is because here I need some statistics to actually calculate it. And basically it doesn't appear yet. You need to do something else for it to appear. And this is here an estimate of the pressure in your system. Okay? So this is a way to play a bit. Now what you can do is basically reset again, and you can increase, in fact, and change the grid size, right? So here you see you've got more cells, and you can of course play differently. And in particular, you can also change the size of the disk that you want to insert. Okay, so here you see it has more of a circular shape, and you can run the thing. Because you have many particles, it will become very slow, basically above 30 or 40 particles. So what you can do is simply increase the speed of the simulation, and then you will see it actually go faster. You can continue to increase it, in fact, if you are not pleased, and then you will see proper diffusion of a drop of ink into a bigger system. What you see is that basically the energy is lower. That's normal because that's the total energy of the system, and I have more particles, so this is actually lower. What you can play with, still with the same system, is basically I will do a reset here, I will put a drop here, and you can play a bit by changing also the number of subdivision you want to put on horizontally, if you will, in this lattice. And what it will do is basically give you an estimate of the probability density of your particular droplet and your particular solid. So once you've got this, what you see is that you've got 6 here, and what you see is that the entropy is higher up. Okay, sorry, we have set 7, and here's the entropy is higher up, and the reason why is because we start already with many, with a kind of certainty in various areas. So for instance, it's quite certain to be there, quite certain to be there, quite certain to be there, uncertain to be there, etc. And this makes the Shannon entropy quite low, but actually still high, because they are more or less of the same height, if you will. And so if we run this thing, what you will see is that the entropy increases as we normally expect. Okay, so it increases, and one can actually check that in the long run, the actual, and we can check that right now. In fact, I will just increase again the speed. So in the long run, it will actually tend toward basically, if I'm not mistaken, it should tend toward log of 7. Okay, so that's basically the idea. The value of the Shannon entropy associated to this is 192. Okay, so this also demonstrates a statistical kind of law that explains how how increase in entropy is related to loss of information about a particular original knowledge or configuration that we knew about. Right, so that's more or less it. Now there are ways to play with temperature. So for instance, we can quench, let's say, a little bit to 2.5, and it's obvious that basically the system starts to clusterize. If you start to become epileptic because of these cells, I'm not sure it's actually much better, but you can actually switch off the grid and actually see things a little bit differently. So that's more or less the way how to play with it. There are various data that can be printed to file. If you actually click on print config, it will print the configuration that is displayed at the moment here. If you click on print entropy, it will actually print this particular thing, and I think, and also, if I'm not mistaken, it will also print this particular thing, and in particular, it will also print the value of the frequency here to file. And if you repeat that multiple times, you can actually print a map, a two-dimensional map of the histogram here of the probability density evolving in time. Okay. And to finish, if you print entropy, then you've got loads of data that can be printed to file, and I think that's about it. So this data is in particular very useful to retrieve, for instance, the phase transition, the critical point, and basically the binodal curve for the liquid gas coexistence. So that's about it. Just to finish, I will simply show that we can actually consider quite big systems. So just to show the grid, this is actually, I can even do better. It becomes eventually quite slow, but just to show that we can do quite good. And then in that case, you can try to mimic a bit like a real droplet experiment, where you would have an actual, you've got now 1649 particles, and then you switch basically off the grid in that particular case, and we can try to simulate how these things behave. I could try to actually let it go, but I want to make it diffuse. So you can have a look at it. Of course, now it's not like really continuous, and you will see it simply diffuse as basically a movie that you see on YouTube of ink diffusing in water. Okay, so here you can see, of course, there is a distribution that changes as time goes, etc., etc. Okay, and the corresponding entropy is increasing as well, etc., etc. Okay, so that's how this particular piece actually works, and very soon I intend to put it somehow available on the internet, but so far I don't know how. So that's basically it. Thank you for watching, and see you next time.